Good morning, everyone. Welcome to this presentation about the evolution of the MXL SDK. So the MXL project has been established a few months ago, and it evolved rapidly from an idea to a production-ready SDK. The agenda for today, we're going to cover why MXL, why does it even exist? Why do we need MXL? A quick project overview or project timeline, the current state of the SDK, and the upcoming features, as well as parallel activities from the EBU DMF that are related to the MXL project. So why do we need MXL? What is this all about? The main reason why we need MXL is that the execution environment is changing drastically. We've been living in a world in the past where we had fixed function media devices, fixed function servers, applications, or software that were interconnected by transmission protocols such as SDI, 2110, 2022-6, NDI, SRT. We've been very good at creating lots of interconnection protocols. We're going into a dynamic world, a world where we build dynamic media facilities, where software is broken down into small media functions. You have an encoder, a decoder, a graphics engine. All of this can be broken down into smaller components, microservices. These components, they can execute on bare metal, in Docker, in containers, in Kubernetes, still on COTS compute, or in the cloud. So the environment, the execution environment has changed drastically. And we need something that is applicable, that is suitable for this change of execution environment. It makes little sense to encode a transport stream between containers, encode, decode, and waste CPU cycles and resources to move data around. We need something better, something that is applicable for this new dynamic media environment. I was talking about dynamic media facilities, the MXL project, media exchange layer. It's a layer in a stack, in a full stack defined by the DMF, the EBU DMF project, Dynamic Media Facility. If you're interested, the latest reference architecture for the DMF project has been published a few weeks ago, I think a week ago, so it's available for public consumption. This layered architecture here is built on standard COTS, standard hardware, standard operating systems, container platforms, so we're not reinventing anything here. We're just using generic execution environments. The media exchange layer is the first layer here, the bottom layer here, that defines how to exchange the media in this kind of an environment. The upper layer will define more additional functionalities such as the application UIs, the resource limits and requests, how do I provision my environment, and so on. Media exchange MXL is specifically limited and constrained to the I/O. It doesn't try to cover the provisioning, the execution environment. It's really just the I/O. In a dynamic media facility, you also have cross-cutting aspects, elements that are important that needs to cover the full stack. So you have the layered architecture and you have cross-cutting aspects such as security. You need to cover security from the infrastructure level, your network environment, your encryption, up to the operating system that you have to maintain and apply patches. Execution, exchange of media. You need to exchange flows and grains between microservices in a very secure manner up to the user interface, served to the user in a secure way. So security is a cross-cutting aspect. Control and monitoring as well. You need to be aware of your complex and dynamic media environment, aware of the health, the status of every element in your system. So every software element, but also the full stack underneath your media functions. And the provisioning requirements. How do I deploy this? It's highly dynamic. It's more complicated than traditional shrink-wrapped solution. If I ship a card, it's easy to deploy a card. If I have something highly dynamic, many things can go wrong, so you need to be in control of your deployment environment. And there's a DMF track that is covering that specific project here. Quick overview of the MXL project timeline. So MXL moved fast. So there was an idea, November 2024, a few key vendors met together in Geneva, kicked off a project, kicked off what we call the Tiger Team, basically people involved on a weekly basis on getting this thing off the ground. And literally a couple months later at NAB last year, we already had the first milestone, the first demos, private demos, just to show and demonstrate the concepts. Last summer, we became a Linux Foundation project. So the MXL project is under the Linux Foundation umbrella. Now that we are under the Linux Foundation umbrella and we have the charter in place, we also have the code. The source code is open. It's Apache v2 on GitHub, and everybody can download it, try it, and use it in their own projects. So at IBC, real multi-vendor interrupts, the first ones, release candidate in December, GA in February, and there we are now at NAB with multiple vendors doing interrupt here on the AWS booth, in multiple vendors' booths as well. How did we manage to do that in 15 months? There are multiple reasons for that. The model has been proven for a long time. Many vendors have been doing shared memory media exchange over multiple years, so we knew it could work. We just had to adapt the model to a containerized environment. We had lots of very actively involved members who really contributed to this project. So there was a real need in the industry for having such an interrupt API or mechanism. But I think the key is that we are focusing on living code. The measure of success of this project is an SDK that can be used by vendors directly in their own application. So no specification written in 17,000 pages, and then you have to read it back and re-implement it and interpret the spec and then do interrupts that may take multiple months or multiple years. The measure of success of this project is living code on GitHub that you can use in production in your product. And this compresses the whole cycle from years of test, interrupt to a couple months, and we have something that can be used, that is already used by many vendors. So just to show the level of adoption of MXL, these were the key initial founding members of the project that were present at the EBU meeting in Geneva: broadcasters, manufacturers, industry organizations. So already quite a wide group, and literally over time more people join. So we have containers from new vendors that are joining the project. So it's extremely exciting to see that there's lots of buy-in from the whole industry, really. So there was a need, and we have the SDK now, and people are joining very rapidly. I'm going to do a quick overview of the MXL SDK. I don't want to go too much in the details of the SDK, but maybe just explain what we were trying to achieve. We wanted an SDK that would allow media functions to exchange data on the same host across containers or across machines on a fast network, on a fast LAN. It had to be performant. So no encapsulation, no decapsulation, no encoding, decoding. It had to be very, very fast. Ideally, zero copy, direct access to the media. It had to cover video use cases and audio use cases as well. So for video latency, having a couple lines or a couple frames, sometimes it's acceptable. For audio, you may want to go down to 125 microseconds. So it had to be flexible with the latency of individual flows. We wanted this to run on a wide variety of execution environments, from bare metal to Docker container, Docker Compose, or Kubernetes. So it had to be flexible. We wanted to have something that does not impose a large platform on the implementers. And I think that's one of the key reasons why it worked well. We're not bringing gigabytes of legacy or vendor-specific DLLs or shared objects that you have to bundle with your project. It's really just a small DLL or a small shared object. You link against it, and you are MXL compliant. It makes adoption much easier than having to buy into something that is very big. We leverage existing terms and concepts. the JT-DMF reference architecture, flows and grains, identity and strong identity and timing. So we reuse existing concepts. If we can reuse the existing object definitions like a float, we just reuse it. Why reinvent these concepts? We wanted an SDK, no specification, small library. We wanted this thing to be secure because this is going to be used in the cloud with multi-tenancy environment. I have customer A and customer B all on the same system. I want to make sure that there's a way to separate, make the flows invisible or this customer to that customer. So strong security, making sure that you have proper separation of flows. And we also wanted to make sure that it works well with devices such as GPU, FPGAs. So being able to create these shared memory and leave the memory on GPU memory, again, as an optimization. We ended up with a simple SDK. It's not that big. C++20, simple C API, based on the concepts of flows and grains where the flows are stored in shared memory ring buffers. So in this industry, we're really good at thinking in terms of senders and receivers. We're pretty bad at thinking in terms of direct access. So the first mental leap with MXL is you have to think about reading and writing existing data. The data exists on your server. Why are you sending it to another container? That's a key concept in MXL. You're just giving access to data that is already available on your server. It's elementary streams. So if you have video, audio, ancillary data, each stream gets its own individual ring buffer. The SDK internally, when it accesses a flow, it literally just memory maps a virtual file on file system, which is the flow, and access it without even memory copying. It's direct access to the flow. So how do you exchange memory between containers running on the same platform and keep it secure? So engineering hat on. So typically you would use shared memory primitives, mutexes, condition variables, POSIX, shared memory, system5 shared memory. We can't do that. We can't give access to the host interprocess constructs and primitives to the container. I'm pretty sure that AWS wouldn't like us to require IPC access on their EC2s if you run it in a container. So we had to keep everything airtight, yet share memory and share synchronization across containers running on the same host. So how did we do that? We achieved it by treating memory, so the flows and grains that you want to share, as virtual files in a tempfs folder. So tempfs is a volume, is a type of file system that is really just structuring your RAM as a file system. So it looks like a file system, but it's really just RAM. And so it's structured RAM. It's not adding overhead, but it presents itself as a folder with flows and grains stored in subdirectories in that folder. And now you see that if you have a folder, it plays really, really well with containers. The folder becomes a volume that you explicitly map in a container. So I have this multi-viewer here. It needs to access these flows. I map this volume, what we call the MXL domain, as a tempfs volume inside that container. And at execution time, it can only see these flows. You can even mount the volume in read-only mode. Since I'm a multi-viewer, I'm not supposed to touch the flows. So I just mount the multi-viewer, mount the folder, the domain, as a volume in read-only mode, and you can access the flows without copying anything at all. So extremely efficient, maximum security, minimal privilege. Since it's a tempfs, it looks like a file system. You also benefit from the normal file system primitives, such as iNotify. You can be notified when something changes in it. You get the Unix groups and users, files permission, read, write, traversal, and so on. So you leverage all of that for your flows and grains that looks like a file system, but it's really just memory. And all of these flows grouped together is called MXL domain. Internally, the ring buffers use the concepts of the same concept as 2110. It doesn't really need PTP, but it's based on the same concepts. So the first grain ever written in the ring buffer was in January 1st, 1970, the epoch. and then you just increment in your ring buffer by your grain duration. So if my video frame is 1080p 59, that would be 16 milliseconds. You just increment by 16 milliseconds, and you roll in your ring buffer, and you know for the current time where the grain should be. It's a simple modulo operation. You know exactly where you should be in the ring buffer very easily. Again, a mental leap. First mental leap, it's readers and writers. The second mental leap is you have access to history. You can read back in time. So if you're sending multiple cameras and they end up going through different paths on the internet or even internally, and one camera and the other camera, they don't have the same latency, but you know when it was captured, if you have the origin timestamp of the shutter time of the camera, when you write in the MXL domain, you can actually write back in time because you know it was captured 2 frames ago, so you write it where it shall be. And then in your multiviewer, you have the luxury of going back in time and line up all the feeds. So the ring buffer duration, what we call the history duration, is usually half a second, could be a second, 2 seconds. It's really just RAM. So if you have RAM, and now RAM is really cheap. If you have enough RAM, you can configure your ring buffer duration and use more history and go back even further in time. So this is the second mental leap. You don't have to work as a real-time application. It's all asynchronous. You can bounce frame across microservices, produce new grains faster than real time. And sometimes if you have to apply a logo, scale down, mix with something else, all of these operations can be collapsed in a couple milliseconds because each of these steps are really fast. Since you're not locked to real time, you can combine these operations and get them to execute faster than real time. So you're not introducing delays and latency when you compose functionality, for example, in a multiple ME switcher. Everything can be done faster than real time within this window of time. And your final frame comes out maybe at the next time boundary. So you have the luxury of going faster than real time and going back in time as well. What are the features of the SDK? SDK 1.0, we have a stable API for video, audio, and ancillary data, including alpha channels, so fill and key. We have a stable API for readers, writers, and synchronization of flows and time management. We have tools and examples, GStreamer plugins, Rust bindings. So a nice company provided, a nice gentleman here provided Rust bindings because they are using Rust in their company. So again, it's an open source project, so contributions are welcomed. So we have Rust APIs for the SDK. What's coming next? MXL fabrics allowing you to connect multiple machines on the same LAN and replicate ring buffers from machine A to machine B using accelerated technologies such as RDMA if you're on the ground, or if you're in the cloud, it could be EFA on AWS. And this is a demo that we have here at the moment on the AWS booth. Replicate flows across nodes using acceleration technologies, even in the cloud. Again, I said replication. I didn't say sending and receiving data. I replicate the flow. And this is important, another mental leap. I have my flow called ABC. It has a GUID. So GUID ABC. And I have a media function here that needs to access data. You're not sending the grains one by one or asking the grains one by one on this other side. You tell the orchestration layer to establish a link, a fabric links that replicates the whole ring buffer on the other machine. So as a media function, if you're trying to read the flow, you don't need to worry about the provenance, the origin of the flow. It's there. It's just a local flow for me. It has the same GUID, the same payload. It's binary identical. But as an application writer, you basically don't think about networking. It just gets there for you. So quick overview of MXL fabrics. Basically, it bypasses the operating system. The transfer is done by the network adapter, which is, again, much better than sending small UDP packets through the network stack and down again. Again, maximum performance. We have parallel activities that happen at the moment through the JT-DMF group and the AMWA group. So end-to-end synchronization. So how do we describe the timing model in in MXL? So what are the timestamp? What do they mean? What is an origin timestamp? What if I have two different environments that are not synchronized? How do I frame sync between these environments? So end-to-end synchronization across DMF islands. This is being handled by Andy at Appear. Compute resource management handled by Riddle, led by Riddle. How do we provision, deploy, allocate the resources? Flow connection. Now that if we map our flows to NMOS ISO 4 and ISO 5, how do we get ISO 5 to establish the connections between the receivers, senders and receivers in the NMOS world, but in the MXL world, it's really just readers and writers. And then there's also a business track. How do we license this kind of code? How do we bill? How do we meter? Is it pay as you go? Is it subscription? How will this work? So there's a business track as part of the JT-DMF project. Gareth here is handling the NMOS with MXL project. the NMOS with MXL project. So how do we map the MXL concepts that are unique to MXL in the NMOS world, such as the MXL domain, the domain ID, what does it mean to start and stop a flow, and so on. So the well-defined, well-described mapping between MXL and NMOS. Any questions? I think we have a microphone here, so.
Hello. Now SDK first support only V210 format.
Yes.
What's the plan for the future?
So that's a very good question. We want to promote interoperability. We wanted to limit the operation points. So and this is like a religious war all the time. So I want 12-bit, I want 16-bit, I want 10-bit, I want RGB. To get to a point where we can do interrupt early and get the project off the ground, we started with V210 as the first 4cc, and we invented a 5cc, which is V210A, which is V210 buffer plus alpha at the back, enough to do broadcast. So it can cover HDR, SDR, PQ, HLG. So good enough for broadcast. In the future, maybe in a couple years, we can release the tension a bit and try to add more formats. But for video, you're right, it's V210. For audio, it's float 32. So float 32, no end audio. For production, float makes lots of sense if you need to do micro fades and prevent clicks and pops. Everybody processes internally as floats. So that's why we stuck to floats. And for ancillary data, we didn't reinvent anything. It's really just 2110-40 payload without the headers. So most of the headers stripped away. So it's on purpose limited to V210 just to promote interrupt. There was a second question.
I wonder if you'd comment a little bit about just the positioning of MXF with everything else. So I've gotten a few questions here.
Yeah.
I think I understand, but like we have SMPTE 2110, we have IPMX, and these all have 3-letter names.
Yeah.
I believe that they all fit together, but I wonder if you wanted to take some time to like position these things are not replacing each other.
They're not replacing, they're not competing against each other. So the MXL SDK and the model, the pattern used by MXL is to exchange data in an execution environment that is running on COTS hardware, sharing the same resources. You still need the I/O protocols to send into that island and send out, so to receive and to send. So 2110, it will still be needed to bring signals in, to send signals out. Same thing for even SDI is very relevant in this world. So they're not competing. They're just answering a different problem or finding a solution to a different problem. There was another question, François? You raised your hand or no? No? Okay. Good. Yeah. Thank you.